Okay, these are the new packets we just picked up. If you go back to the beginning, recall that we did put our name right in the front. If you didn't get one of these packets on the first day when I passed them out, they're under the front table where we pick up the worksheets. Look for the big packets underneath that are hanging out there. So go grab a packet if you didn't get one. Otherwise, remember that we did this first task digitally on our Google Classroom. So all of this is already done digitally. Okay, so we already did all this. We did a whole bunch of Desmos graphs. And so now we're getting down to lesson 2, which is on pages 9 and 10. Your assignment today is to do pages 9 through 15, so let's get started. I'm going to zoom in here now on page 9. So without using technology, match each of the equations with the graph of the functions. Be careful that there are more graphs than equations. So for A, notice that we've got an x squared minus 3. So taking a quick peek at which of these graphs look like they have that shift. What shift would this look like? You got it. This would be a shift down 3. So looking at these graphs, which one went down 3? Do you see that number 2 is the matching graph? Okay, next, here's an x minus 3 squared shift. So remember that x minus 3 is a shift right 3 of the vertex. So looking at which of these has a right 3 movement, do you see that it's this guy right here? So there's our matching. We used number 4. Next, we have a 3x squared. That means it's 3 times as fast as our parent graph growth. And so which one looks narrower than the parent? You got it. It's graph number 3. Number 3 is narrower than the parent. It's going up 3 times as fast. And finally, we've got the 1/3 x squared for part D. Part D is going to be wider than our original parent. It's going up 1/3 as fast as usual. And so that would be number 5. So looking at all that's left, why wasn't this our answer to anything? This was back 3, 0, and it's the normal parent graph growth. So this one would be an x plus 3 squared quadratic. And so none of those it wasn't used for any of those. So that was your warm-up, your jump start. Let's go down. Our learning focus for the day is to write equations for functions that are transformed from the original parent. It's to find efficient methods of graphing these transformations. And it's to note what happens to the graph of x squared when more than one thing is applied. So that was page 9. We're now moving over to page 10 in your little packets there. So in the previous lesson, you learned about transformations of the graph from the original parent graph of x squared. In this lesson, you're going to be writing equations and graphing functions. So writing equations and graphing functions that have more than one transformation. It will be a lot easier if you know a few of the points on the y equals x squared graph. So our parent graph y equals x squared is right here. And they're asking you to identify the vertex. Okay, well, we got that. That's 0, 0. And then a couple of the other anchor points. Notice that we have this out 1, up 1, and out 1, up 1 in the other direction. Out 2, up 4, back 2, up 4. Out 3, up 9, back 3, up 9. Why are those the anchor points? Because 1 squared gives me an output of 1, because 2 squared gives me an output of 4, and 3 squared gives me an output of 9. When I'm graphing and I'm doing the same stretch, the same growth, I go out 1, up 1. out 2, up 2 to both sides, out 3, up 3. This is my normal parent growth. All right, where is my line of symmetry on the normal parent graph? It's going to go straight down through the middle of the vertex, right through our origin. So in this case, it's through x equals 0. Okay, write the equation for each problem below. Use a second representation to check your equation. So this one's like a little word problem here. It says the area of a square with side length x. So draw me a square where the side length is decreased by 3 and the area is multiplied by 2. And then 4 square units are added to the area. So here I've got my x by x square, but it said that the side length is decreased by 3. So we're going to cut into the square 1, 2, 3. What that means is we're subtracting 3 from that edge, but this is a square, so the same thing has to happen on this time. Cut in 1, 2, 3. So we're subtracting 3 from this edge as well. There's my square decreased by 3. So I'm going to highlight this. That's representative of that part. Then the area is multiplied by 2. So I don't just have one of these. I got another. So draw me that x by x square. Cut in 3. Cut in 3 from the other side. And there's my second one. So the area being multiplied by 2. Let's use a different color. Is that I've got 1, 2 of these now. Finally, 4 square units are added to the area. So these down here are these little square units. So we're just going to put 4 little squares on the very end with little ones inside. Those are the 4 square units. So it's 2 of these and plus 4 little units down there. So this is my visual representation of what that said. Oh, by the way, let's go highlight that. I'm going to use pink for these little 4 square units. Okay, what would my equation be for this? It would be 2 times the quantity, x minus 3 squared plus 4. The 2 comes from the fact that we multiplied this by 2. The x minus 3 is my x minus 3 squared from the picture, and then the plus 4 comes from the end there. This is my function. How'd you do? All right, I'm on page 11 now. So look at these little page numbers down here. Okay, they gave me the picture of a graph right now, so let's go work backwards. Can you identify that vertex? Take a minute, pause the video, tell me what that gives you. Okay, did you say it was right 3 and down 1? Did you get a vertex of 3, negative 1? Now, we have this new vertex form of a parabola. It's plus or minus a, x minus h squared plus k. And I know this is going to be a positive orientation because my graph is up. I'm going to come back to the a here in a second. It's going to be x minus 3 squared minus 1. This 3 comes from right there, and this minus 1 comes from right there. Now, is this the same stretch as the normal parent graph? Is it going out 1, up 1, or is it going up differently than the normal parent? So here I go counting, out 1, up 1. It's not the same as a parent. It's out 1, up 2. Out 1, up 2. That means that my stretch on this graph is 2. And that's it. That's our equation. How'd you do? This next one gives us a table. This is moving down 5, down 3, down 1, up 1, up 3, up 5, 7, up 9. And then notice that there's a constant second difference of 2. All right, so now we're going to go try to build a function from this. We know there's an x squared in it. Do we have the 0 term here? We do. So let's go see. And then by the way, we can tell that since this is the constant second difference of 2, half of the constant second difference is my a value. So half of 2 is just 1. So we know this is a 1x squared. That comes from this rule right here. And we know that the 0 term is 0, negative 1. Now we're looking to see if the infamous b comes into this equation, or is this enough? So let's test out some input outputs. So if I were to say f of 1, notice right here that I'm supposed to get an output of 2. So let's plug in 1 squared minus 1. 1 minus 1 is 0. That does not give me the output I need. I need a b value. So here's where we have to work backwards to solve for b. So check this out. Another way of saying f of x, you got it. It's a y. Y equals x squared plus bx minus 1. I'm trying to solve for this b. This is the first time we've done this because all we've dealt with so far are simple quadratics. So if I knew what an x and a y were in this equation, couldn't I solve backwards for that b? Well, guess what I got a lot of, people? I got a lot of xy coordinates. You can use any xy pair from this table. Ms. Sanchez loves 27, so I'm going to use the 2, 7 pair. So here I go. My y value is a 7. My x value is a 2. My x value is a 2. And there's a minus 1 at the end. The only thing I'm leaving as the unknown is this b value that I'm trying to solve for. 2 squared is 4. 4 minus 1 is 3. Subtract 3 from both sides. I get 4 equals 2b. I get that b equals 2. So that means my final equation is x squared plus 2b. Oops, just kidding, we got the b. Plus 2x minus 1, and I'm done. We plug that b right in right there. Okay, are we going to practice this some more? You betcha. But this is our first exposure to how we work backwards to calculate a b value for the more complex quadratics. Okay, let's go look at the next page over here, number 5. I'm trying to get the equation of this. So let's start with that vertex. Pause the video, take a minute. Get me that vertex. Check out the growth. Is it the same as the parent or different? Okay, did you notice that vertex is back 3, up 4 from the origin? So putting that in, by the way, since this is a downwards facing parabola, are you okay that this is going to be a negative this time? There should be a negative up front. I'm not talking about the a value yet. Let's just go plug in the vertex. Notice this is a -3. So x minus a -3. Are you okay with that turning into a positive here in a second? And then it's +4. Now let's go talk a value. All right, what's this one doing? This one is going out 1, down 1. That would be the normal parent. This is not going down a full 1. I can't quite tell if that's down half or what is that. So let's go check out the 2 and see if we can tell. Out 2 would normally be down 4, but this one stops right here. Out 2, down 2. Can you tell that that's half the normal parent? For example, out 4 would normally be down 16. And this is only down 8. So this is half the normal parent growth. And that's our equation. Let's write the whole thing out. F of x equals -1/2 x plus 3 squared plus 4. How'd you do? Graph each equation without using technology. Be sure to have the exact vertex and at least 2 correct points on either side. You know, Ms. Sanchez wants you to have at least 4 other points besides the vertex, but you do you. Okay, so on this one, if there's no horizontal shift, there's nothing with that x in parentheses. Are you okay that that's no change, no horizontal change? And so that means my vertex is starting still at 0. And then it says +3 at the end. So this is actually going to go up 3 for this shift right here. And this little negative orientation, that's telling me that the parabola is going to be upside down. So go ahead and get a graph ready. By drawing in some axes for me. Here's my x, here's my y. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, we're labeled and scaled. Here we go. So we're starting at 0, 3. Go put your dot. That is my vertex. Remember that this is going to be a downwards shaped parabola. So that should be my maximum there. From there, it's growing down at the normal parent, right? -x² is just a stretch of 1. The growth is the same as the parent graph. So what does a parent graph normally do? Out 1, down 1. Out 2, down 4. Out 3, down 9. And connect it. You should have a downwards facing parabola that starts at 0, 3 for its vertex. That's also its maximum. And that is growing downwards at the same rate as the parent graph. All right, let's graph g of x. Okay, what's my vertex, my starting point, my critical point of this parabola? Take a minute to write that out. It's staring at you right here. All right, how'd you do? Did you get -2, -5? Did you remember that that sign is opposite? So let's go back to down 1, 2, 3, 4, 5, and put our dot. -2, -5. There's my vertex. From there, the growth is the same as the parent. So going out 1, up 1, because 1 squared is 1. Out 2, up 4, because 2 squared is 4. Out 3, up 9, because 3 squared is 9. Out 4, 16. See if you can fit it on your graph. Otherwise, that's good. And you're done. There's that vertex, there's that growth, the same as the parent growth. All right, last graph number 8. Grab that ruler and go put that axis on there. All right, see if you can identify the vertex this time that's staring at us right here. Did you get +1, 2? Good, go put a dot. From there, we're counting the growth of a stretch factor of 3. My A value is 3. So this is growing 3 times as fast as the parent. So normally it goes out 1, up 1 in the normal parent. So what would 3 times as fast be? Out 1, up 3. Out 2 is normally up 4. 3 times that normal 4, 3 times 4, would be up 12. So we're now going to go out 1, up 3, and we're going to go out 2, up 12. 3 times as fast as the normal parent. Here we go. Out 1, up 3, out 2, up 12. All right, I can only get up to 7, so I'm going to redo my graph. If you already did yours and you can only get those 3 points, that's fine, but I want to show you more points on mine, so I'm going to adjust it right now. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Nope, I still didn't make it high enough because we got to start out at 1, 2. All right, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 6, 7, 8, 9, 10. 11, 12, 13, 14, 15. 1, 2, 3, 4, 5. Okay, this time we should be able to fit it all on there. We're going to go out 1, up 2. Here's my starting point. From there, we count the normal growth would normally be out 1, up 1. We're going to go out 1, up 3. And out 2, up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Reset back to the vertex, out 2, up 12. All right, mine looks better. You could have left yours alone. It's up to you. Connect that graph. All right. Given this formula here, what is the vertex of the parabola in this formula? We see that H, we see that K. So the vertex is HK. What is the equation of the line of symmetry? Oh, we forgot to put all the lines of symmetries. I'm going to go back and do those right now. It's x equals the h value, whatever that x value is of your vertex. Can you tell if the parabola opens up or down? Yes. If it has a positive in front, it opens up. If it has a negative in front, it opens down. How do you identify the vertical stretch? The a value in front of the x squared tells us how fast our graph is going compared to the parent. All right, I'm going to go through with a yellow gold highlight to put in all these lines of symmetry. Straight down, actually, I'm going to go get, let's go get a purple. Oh, that's way too thick. Okay, I guess I'm back to just using the gold. So here I go, drawing a dashed line of symmetry straight down through the vertex on this graph. Drawing a dashed line of symmetry straight through the vertex on this graph. Drawing a dashed line of symmetry straight through the vertex on that graph. And this one's right on the axis. Straight line of symmetry straight through the axis on that one. Okay, we forgot those lines of symmetry. Thanks for going back for me and adding those in. Okay. Does it matter in which order the transformations are done? Explain why or why not. So they're asking if you've got this x minus 3 squared plus 2. Does it matter if I go right 3 and then up 2? Or if I go up 2 and then right 3? What do you guys think? Say yes or no, and let me know if you think it matters what order that happens. Finally, looking at this ready for more, it says think about applying the transformation to this parent function, 2 to the power of x. What point makes sense to use as an anchor point on this function? So we've got f of x equal to 2 to the power of x. Well, what's the breakdown of this function? It's a function that begins at 1 and is multiplying at 2 to the x minus times 0. So your starting point on this table would be 0, 1. And then it would be multiplying by 2 each time to build that table. So what point makes sense to use as an anchor point on this function? I would say using that point of 0, 1, the y-intercept, would be a good anchor point. What do you think is the equation of the function with a horizontal shift left 3? I would take my original function and to do a horizontal shift of left 3, gosh, sorry guys. Okay. It means that I'm just going to put a +3 change to that x. It's the same thing as the function we are currently doing, where if I want to make a horizontal change, that change needs to be made to the x. Finally, how does the horizontal shift work like the horizontal shift on x squared? They both need to be made to the x and have opposite signs, meaning a left shift shows up as an x +3 in the equation. All right, looking at these vocab words, when I say them, do you know them? Vertex is the critical point of your parabola. We now know that its letters are h, k, and we also know that it is the minimum or the maximum of your graph of the parabola. The line of the symmetry goes straight down the middle of your graph, and it's the line that divides the graph in half. The vertical stretch is your growth compared to your parent. Opening upward is our positive orientation, and opening downward is our negative orientation. Do all those words sound familiar to you? Quick graph method for graphing quadratics, the out one, up one method, out two, up four method, and then growing hours compared to that parent graph. How'd you do? All right. I'm now on page 15, A, B, and C. Let me see if it had the little directions up here on page 14. So I want you to pause the video at this point and try to graph these on your own, and then play the video to check yourself. Okay? So let's get these ready. Actually, this one I'm going to put more in the middle. Okay. All right. I hope you paused this video. Let's see how you did. The vertex of this first one, you got it. Do you see that it's 4, -3? So we go 1, 2, 3, 4. Oops. I need to fix this. So that I can fit that vertex on there. All right, so let's go put that dot. right 4, down 1, 2, 3. All right, from there, my growth is that invisible 1, that same as the parent graph. So I'm going to go right 1 up 1 on both sides, right 2 up 4, right 3 up 9, and right 4 up 16. Woo, I just barely made 16 on mine. How'd you do? Can yours fit? And then connect that parabola. Oops. Okay, let's try that again. Go ahead and connect this parabola. Okay, and then end with that line of symmetry. I'm going to draw a dashed line straight through the center of that vertex. My line of symmetry goes through x equals 4. How'd you do on graphing that? Okay, on this next one, do you see that it's going to be a downwards orientation? Sorry, there's the dog that's barking. And my vertex is -2, +5. We can see it right there. So back 2, up 1, 2, 3, 4, 5. That's my vertex. In this case, it's going to be a maximum because this is a downwards orientation. Oh, the puppies are talking to you guys. Okay, -2, 5. There's my starting vertex. From there, it's growing downwards. Out 1, down 1. Out 1, down 1. Is she outside?
Yeah.
Go get her.
She's killing something.
Out 2, down 4.
Hey, what the hell are you? Let her in. Stop. I don't want to touch the doorknob right now.
Out 3, down 1, 2, 3, 4, 5, 6, 7, 8, 9. And then let's connect it. All right, and let's draw that line of symmetry, a dashed line straight down through the center of that vertex, through x equals -2. That's my line of symmetry. How'd you do? Okay, last, my vertex is -1, -5. Did you get that from this? How'd you do? So -1, -1, 2, 3, oops, I didn't leave enough room again. Okay, here I go. Back 1, down 5. It's going to be way down here. Okay, go put that first dot at -1, -5. Oh, we already did. From there, the parent graph would normally be out 1, up 1, out 2, up 4, out 3, up 9. But this graph is going up 2, 2 times the normal parent. 2 times as fast. So my outputs are going to double. They're going to be 2 times the normal outputs. So here I go. Out 1, up 1 is going to become out 1, up 2. 2 times that 1. Out 1, up 2 would normally be out 2, up 4 is going to go up 2 times the normal. 4 times 2, it's going to go out 2, up 8. Out 3, up 9, double that, is going to become out 3, up 18. So from our original dot way down there, go out 1, up 2. Out 2 is normally up 1, 2, 3, 4, but this is going up double, 5, 6, 7, 8. Out 2, up 8. And out 3 would normally be up 9. Remember, I'm resetting back to the vertex. 1, 2, 3. 1, 2, 3, 4, 5, 6, 7, 8, 9. That's my usual. This needs to go double that. 10, 11, 12, 13, 14, 15, 16, 17, 18's right off the graph. You don't have to do it if you don't want to. All right, and then connect that graph, and let's draw in that line of symmetry. How are you starting to do on the growth part of these? Because I know you got the vertex down. Oops. Look at that skinny graph, skinnier than the parent. And then drawing that line of symmetry straight down the middle vertex. This time my line of symmetry is straight through x equals -1. All right, that's it. That's page 15. Are you exhausted? How'd you do?